Have you ever stopped to wonder what's really going on inside the tools we use to write code? It turns out there's this quiet intelligence at work, solving these little puzzles hidden right inside the lines we write, long before our programs even get a chance to run. And it's a really fascinating process, something that's totally worth digging into.
Okay, so take a look at this. On the left, we've got a pretty simple piece of code. It's a perfectly logical sequence of instructions a machine could follow, no problem. But a modern compiler, it sees an opportunity here. It looks at this and creates the version on the right. See what it did? It removed that redundant step of storing a value only to immediately load it right back. The program's result? It's exactly the same, but now it's just that little bit more efficient.
And that, right there, brings us to the big question for this whole explainer. Really, how does it know it's okay to do that? How can it be so certain that just yanking out those steps won't break anything or completely change the outcome? This isn't just a lucky guess. It's actually a process of really deep understanding.
To answer that, we kind of have to shift our whole perspective. We need to see our code the way a compiler does. And, well, it's not a simple linear reading like we do. It's more a process of deconstruction and reconstruction. It's all broken down into two major phases.
And this is a great way to picture those two halves. First, you've got the analysis part. This is where the compiler just breaks the program into tiny pieces, gathers a ton of information, and builds up an understanding of what's going on. Then you've got synthesis. That's where it uses all that understanding to actually build the new, better machine code. And the secret to our whole question? Well, it lies completely in that first step, the analysis. So the main technique they use in this analysis phase has a kind of formal name. It's called data flow analysis. But don't let the name fool you. It's really just a set of methods for gathering information about how values get created and how they travel from one part of a program to another. You could say it's how the compiler gets its vision. Okay, so before a compiler can even begin to analyze the flow of data, it has to do something really important first. It has to understand all the possible roads that data can travel down. Basically, it needs to build a map of the program's logic.
Yeah, exactly. It starts by creating a map. And obviously, we're not talking about a geographical map. This is a map of pure logic. The compiler's first job is to trace out every single possible journey the program's execution could possibly take, all the way from the start to the finish. And creating this map, it happens in a few stages. So first, you can see the code gets broken up into what are called basic blocks. These are just uninterrupted sequences of instructions. Next, those blocks are connected with arrows, and those arrows represent every possible turn or decision the program could make. The final result of all this is what we call a flow graph, and that is the compiler's complete map. So this is where the whole process really shifts gears. Now that it has the map, the compiler doesn't need to do some kind of impossibly complex calculation. Instead, the analysis becomes this really simple but powerful process of just asking the right questions. It's like it becomes a traveler. It moves through this flow graph and just pauses at each block, each little stop on the map to gather some intelligence. So one of the most fundamental questions it asks is about something called reaching definitions. All this means is, at any point in the program, the compiler looks backward and asks, okay, for this specific variable right here, where are all the different places its current value could possibly have come from? And just knowing that helps it spot all sorts of potential problems, like, a variable being used before it's ever even been assigned a value. Now, another key analysis looks in the total opposite direction. It's called liveness analysis. In this case, the compiler looks forward and asks a different question. Will the current value of this variable actually be used again somewhere down the line? If the answer is no, then that value is considered dead. And, well, if a value is dead, there's absolutely no need to keep it around. And that is exactly how the compiler knew it could safely remove that redundant store instruction from our very first example. Pretty cool, right? And this way of thinking about mapping paths and asking questions about the past and future of data, it's surprisingly practical, even for those of us who, will probably never write a compiler. Because it turns out these foundational techniques are incredibly versatile. They go way beyond just optimizing code. They're actually the engine that powers the static analysis tools that find those really subtle bugs in our code before we even run it. They're absolutely critical for security tools that scan for vulnerabilities. And they are the core of so many of the productivity tools that help us all write better, safer code every single day. When you really step back and think about it,
the so-called intelligence of a compiler, it's not based on some unknowable magic, right? It's built on a very calm, methodical process. It just kind of reminds you that truly smart systems are so often built on simple questions, just asked very carefully.
And, well, that kind of leaves us with a final thought to take away. As you're working on your own projects, what are the simple questions you could ask? Questions about where data is coming from or where it might be going. Questions that could help you better understand the systems you build every single day.